Alright, so moving on with the next calculation. Now we've got our 10 milliliters of 0.5 molar acetic acid, and at this point we're going to have 6 milliliters of 0.8 molar sodium hydroxide. So again, stoichiometry is the first step. HC2H3O2 plus NaOH makes NaC2H3O2 plus OH, and we've got 0.005 moles. And now if we take 6 times 6 milliliters times 0.8 molar, I believe we get 0.0048 moles of sodium hydroxide. So that's going to decrease by 0.0048, and there we go, minus 0.0048. Leaves us with 0.002 moles of excess acetic acid, but also this is going to go up by 0.0048 moles for the conjugate base, leaving us with 0.0048 moles of conjugate base. Divide by the new volume, 0.016 liters, and now I've got my concentrations. 0.002, 0.002 divide by 0.016 leaves me with 0.0125 molar acetic acid, and 0.3 molar acetate ion from the sodium acetate. And because it's excess weak acid with a common conjugate base, C2H3O2 at equilibrium with H+. Again, this is because the weak is excess. We're still doing ice problems once we've done stoichiometry first. And this will go up by X, down by X, and mathematically 1.8 times 10 to the negative fifth equals X times 0.300 plus X over 0.0125 minus X. And again, because we're in this point of buffering, we can ignore the X. Now we can't ignore the values there, but we can definitely ignore the X. And when I simplify and solve for X, I get that X equals 7.5 times 10 to the negative 7. And again, that's my H plus concentration, so negative log of that value. And I get a pH of 6.125. Now, a common misconception is that the pH at the equivalence point here is going to be 7, and that's only true on a strong titration. So there's some point, as we're going to see here in a moment, between the 6 and the 6.25 where we're going to pass a pH of 7. The equivalence point is not going to be 7, and I'll explain that as we go through the next problem. So what happens at this point? 6.25 milliliters, we've talked about it already. We've got stoichiometry first. HC2H3O2 plus NaOH, single arrow, NaC2H3O2 plus HOH. We got 0.005 moles, and if I multiply that out, I do believe 0.00625 times 0.8 is also 0.005 moles. So we're at the equivalence point. So show that those are used up, show that those are used up. But we have this common ion, this ion here that's formed. So we had 0, it goes up by 0.005, leaving us with 0.005 moles in a total liter solution of 0.01625. So I've got a concentration of acetate ion of 0.005 divided by 0.01625 of 0.308 molar. And again, we've talked about the fact that this is not going to be a pH of 7. Now, again, one of the things that I've used early on, I've talked about the fact that weak acids and strong bases make salts that are basic. But I also said sometimes that creates a misconception when we talk about it that way, because it makes it a little bit misleading. Some people think you use the strong base to identify the base, but actually the base comes from the weak acid. So the base is that acetate ion. The acetate ion is what's going to make this salt basic. So now we've got C2H3O2 minus as a base. Because it's as a base, I'm going to go ahead and put plus water. Again, with acids, I sometimes don't do that. You could put it, and again, it's not part of any calculation, but it makes a hydronium ion as opposed to an H plus ion. HC2H3O2 plus OH minus, and again, this is what's going to ultimately give us our pH of this solution. Now, prior to any equilibrium, there's not any acetic acid, so up by X to BX, up by X to BX, and this one's 0.308, down by X, 0.308, minus X, and now where do I get a Kb for the acetate ion? Well, I use the Ka for acetic acid to find that, because Ka times Kb equals Kw at 25 Celsius, 1 times 10 to the negative 14. So the Kb is 5.56 times 10 to the negative 10 equals X squared over 0.308 minus X. Now again, you can do the quadratic formula here if you wish. Your A term will be a 1. Your B term ends up being 5.56 times 10 to the negative 10, and your C term is whatever the product of negative 0.308 times 5.56 times 10 to the negative 10 is, and you can do that, but also really low value here, low dissociation constant, low Kb value. So this X is going to be insignificant compared to the 0.308, so I can solve this without the quadratic formula. Just distribute times 0.308 on both sides, and then to get X, I need to square root it. And I get that my X value is 1.31 times 10 to the negative 5th, negative log of that value, and I get a pOH equal to 4.883, 14 minus that value, and I get 9.117. So my pH is equal to 9.117. So plug that in, and it's also probably a good place to talk about an appropriate indicator. I'm not going to use methyl orange or methyl red or bromethymol blue on this. I'm probably going to use something like phenolphthalein, something that changes somewhere closer to a pH of 9. Because if I use one of those that changes at 4 or even 7, it's a good chance I might miss this. Now again, somewhere between 6 and 6.25, that end point for bromethymol blue with a pH change around 7 would occur, but definitely going to do better using something that changes a little closer to the 9 range. Alright, so at this point now we've hit the equivalence point, and now we're going to have excess sodium hydroxide. So we got 6.50 milliliters of 0.8 molar. So stoichiometry first. .005, 0.0052, minus 0.005, minus 0.005 is 0.0002. And in theory, just to mention this, this one will also go up to 0.005. And we'll talk about that, how it's really a non-factor here in just a moment. So we're going to divide this by the new total volume, which is 16.5 milliliters. And I get a concentration here of sodium hydroxide equal to 0.0121 molar, which is the hydroxide ion concentration. Now I'm going to do this real quick, 0.0165. And I get 0.303 molar. In theory, we can still do this as a base. C2H3O2 minus plus water at equilibrium with HC2H3O2 plus OH. However, we have an initial value here of OH, 0.0121. Le Chatelier's principle says by having that this is going to ionize less. This already weak base with a Kb 5 times 10 to the negative 10 is going to ionize even less. So of that 0.303, we're only going to get a really, really small amount when we actually go down here and factor in how much that X value is. Not saying we can't do the quadratic formula here. I'm not saying we can't solve that, but X is going to be really, really small, meaning 99.99% of our hydroxide came from the excess from the sodium hydroxide. It's high enough. Easiest way to get the pH at this point, when you have excess strong, treat it just like you would in the previous problem, the earlier problem where I did a strong titration, and simply just negative log 0.0121 molar. And you get a pOH of 1.91, 14 minus that value, 14 minus, try that one more time, 14 minus that value, is 12.083 for the pH. Now the next one's going to be really, really similar because we upped that to 7 milliliters. So I'm going to go ahead and just do it right here on this page as well. So that's going to be 17 liters. And when we do 7.007 liters times 0.8 molar, 0.0056, it's going to leave us with 0.0006 divided by 0.017. And negative log that value. That value happens to be 0.035 molar. Negative log of that value. 1.452 is my pOH. 14 minus that value gives me a pH at 7 milliliters of 12.548. So notice we're kind of at that 12 range, and it's going to be fairly level, not completely level, but fairly level, as long as we continue to add that excess strong base. 12.083, 12.548.